So I think the plan today was to take a PDB file and see if we can generate some something like simulated cryo-EM data that we could then use with the Gaussian mixture model to do some dynamics analysis on it. It's not quite as interesting maybe as working with real data, but we may get back and do some real data stuff later on too. Let's see. So I made an empty folder here that we could work in. There's always a question, is there any point in working with simulated data? And simulated data is a great way to start something out when you're first developing it. It's also a pretty good way to learn how a new tool that you're trying to use works, even if it's it's not proof that the tool is going to work perfectly in all situations. If it doesn't work on simulated data, then it's probably not going to work on real data either. So I thought we'd do something simple. So I thought, so there are lots of Python-based tools that you can use to manipulate PDB files or MMSIF files, whatever it is you care to work with. A sort of a similar package for crystallography, developed in Paul Adams' group. Phoenix, sorry, completely banking on Phoenix for a minute. So the Phoenix package developed in Paul Adams' group at Lawrence Berkeley National Lab is a nice package for doing X-ray crystallography sorts of things, and it has lots of tools for manipulating PDB files and MMSIF files. Then there's also lots of other Python toolkits out there which can manipulate those things. Honestly, I always favor the most straightforward approach, and for certain things, it's nice to use a graphical tool rather than use Python or command line tool. So I'm going to start out with Chimera. And in fact, I thought we'd play with Chimera X. I'm not nearly as experienced with Chimera X as with Chimera, but it seems like it's reasonably straightforward. And I thought we might use this 1SS8, which is just GROEL. Full subunit, the full GROEL molecule as a test case. It's a molecule that I am very familiar with from previous work with this sort of thing. And you can open local files easily enough in PDB. So these files were showing up. Let me close this again. These files were showing up here is because I've opened them before. So I made sure that this worked before. So you could go to the command line and type open rcsb_bio and then give it the extension number, and it'll load it directly. So this is the full biological unit. If you just say open PDB:1SS8, it'll give you whatever is deposited as the crystallographic unit. If you open rcsb_bio:1SS8, it'll give you the biological structure, the biological unit, which may be larger. In the case of GROEL, the 1SS8 by itself is just a single ring, and the biological subunit is the entire 14-mer. So you can see there are 14 molecules there. Maybe we can change this to ribbon instead of atoms. A little bit easier to see. Okay, so there's 1SS8. So what I was thinking of doing is, what's going on? It's better. What I was thinking of doing is maybe taking one subunit and either shifting it or rotating it or something like that. And then maybe taking another subunit and either having it absent or present. It's a 14-mer, so moving one subunit or getting rid of and putting one subunit back represents less than 10% of the total volume. So it seems like a reasonable sort of test. And if we do it don't do it in adjacent subunits, then we'll be able to distinguish things a little bit better. So I think we'll go ahead and just pick one of them and extract that first. So what we need to do is make the PDB files for the different pieces that we want to put together. So one piece will be one subunit, another piece will be the second subunit, and then the final one will be the rest of it without those two subunits. So I will go here to select chain, and I will pick, so you can see it has A and A2 and B and B2. That's of course because there are actually that's a good question. Why is there A and A2 and B and B2 when we also have bioassembly 2? Right. All right, let me pick A. There's A. And let me pick A2. Okay. Well, if that's the case, then what's this? A. Ah, okay, I see. So it looks like we have the bioassembly, and then we have just the original thing, the original one SSA PDB or something like that. All right, so I will select A, which will be the same thing there. Oops, it's frustrating. All right, so I've selected A, and then we'll go ahead and save. And I'm going to save a PDB file. And I'm going to save selected atoms only. And we're going to call this 1ss8a.pdb. And I'm going to put this in data sim. Okay, so that should only be the single subunit. So then let's pick another one. Maybe we'll pick C, or maybe how about let's pick B2. That way we can pretty easily see it at the same time. It's near A, but it's not quite. It's not, it's not touching A, but we'll be able to see them both together on the screen in the same view. So then let's do the same thing. We'll save 1ss8b2.pdb. And then we need to save the rest. Oops. Seems stuck. What's it doing? Oh, all right, that took a little while. Let me just take a look and see if what we got seems to be about the right size. Sim 6.5 megabytes. All right, that seems too much. Let me try that again. Oh, it unchecked the checkbox. I think that's probably what happened. Okay, that's better. All right, and then we need to save everything except for A and B2. So let's see, how can I also select? This is where my lack of familiarity with Chimera X comes into play. Maybe if I do, no, that's not going to work very well. Graphics map. See if I hold down a modifier key when I do that, if that works. No. Nope. All right, we may have to do it differently. So let's.
Can you, because you can, it looks like it will let you select them all. Is there a way to select them all and then unselect?
Yeah, I mean, I could do it with the mouse. If I, it's hard to select. Well, let me just try it using the command line. So it looks like from the command line, we should be able to say something like select #1.1/A. Okay, that works. So then we could try select maybe comma separated. I'm just kind of guessing here. # 1.1 / chain ID equals B-2. So Chimera X uses the command line a lot more than it uses the mouse and that sort of mouse and that sort of thing. Ah, okay, that worked. Now I have those two selected, and I should be able to invert the selection. Oh, now the problem with inverting the selection is that I may have, well, let me just see what happens when I hit save. All right, so I'm going to turn off that and save selected atoms only, and then we're going to see what we get. One SS8 the PDB. Okay, 74K. Oh, I think it's probably still working. There we go. 3.7 megabytes. All right, so let's close the session and we'll open the individual pieces and see if we get what we're hoping to get. One piece, two piece, three piece. Okay. Interesting how it did that. Let's show the cartoons and hide the atoms. Oh, that's not what I want to do. Hide the cartoons, show, hide those. I may have to change to a preset. Oh, that's weird. Some of them are showing as ribbons, and some of them are showing as cartoons. Clearly, I don't have much of a handle on Chimera X yet. Regardless, it looks like we got what we wanted. We've got the whole thing when we combine the different pieces. And if we turn off A, it's missing. And if we turn off B, that's missing. And if we turn off C, we just have those two. So good. I think we're all good. Doesn't matter what the visual representation is. So I'll learn more Chimera X myself over time. But I think we've accomplished what we were trying to accomplish. We now have these files. So the next thing we need to do is convert the PDB files into some sort of a density representation. Again, there's lots of tools you can do this with. If all you want to do is take each atom and turn it into a Gaussian blob, you can use EMAN's PDB to MRC program to do it. If you're looking to do something a little more accurate that takes things like molecular I don't know if it takes it that far, but at least it takes atomic form factors and stuff into account. Then Phoenix has some tools which will do a better job of that sort of thing. But those things really only have an impact at much higher resolution. So the sorts of thing we're trying to do right here, just generating Gaussian blobs for each of the atoms is fine, with the appropriate density, of course. So we'll use E2 PDB to MRC. Again, we'll just do this from the command line because it's easier and there's a program to do exactly what we're trying to do. And then we say, we'll go ahead and do help. So we see all of the options because there are a few things that we need to provide. So we need to give it the input file, and then we'll make a similarly named 8a.hdf output file, angstrom per pixel. I think we'll go with, let's see, if we do 1 angstrom per pixel, that's going to be like 256. Well, that's fine. We can make the data 256 by 256. So 1 angstrom per pixel, and then we'll make the box size 256. In case there are het atom entries, we'll go ahead and use het. We use dash. Oh, all right. We don't want to use -- center because the overall molecule. Oh, this may be a problem. We'll have to see how this works. It may be that the center of mass of the SS8 molecule isn't at 000. Usually isn't in PDB files. So I should have centered it before I did the extraction. Otherwise, we have to sort of translate it so it goes into the right place in space. So let's see, het center. We'll just try it once and see what happens. Now, this would have been an alternative. I could have used the chains option here, assuming it works correctly. I'm not sure if it would work correctly in this case. We could, but maybe we could try that. Yeah, I'm just trying to think of what would happen if we use chains combined with center, whether it centers first and then only extracts the chains, or whether it does it in the other order. I'm honestly not sure. It's been a long time since I've tried to do that kind of thing. All right, well, let's do --info first and see what we get. I also need to specify resolution. And we're just going to target sort of full resolution, 2 angstroms, 2 angstrom resolution with 1 angstrom per pixel, and maybe we'll say 4 angstrom resolution. Otherwise, it'll look really sharp and funny. So that'll take it out to about half the text. Okay, bounding box. It's 31. All right, let's take a look at the bounding box for the whole thing. Other. Yeah, it's not very well centered. You can see it goes from -116 to 30, -73 to 73. So it's pretty well centered in Y and Z, but it's not centered in X. Yeah, so the X center is off by like 50 angstroms. So if we take a look at that, I'll get rid of the info. And we do need to display. We should see that this other is kind of way off center in the box, right? So you can see as we rotate it around, it's not rotating very nicely. Now, it did fit in the box, and that's actually kind of interesting because the GROYL is about 180 angstroms high, and I said 1 angstrom per pixel. So it should have kind of barely fit into the box, but maybe we just sort of slipped in. All right, we'll do this control panel, and sorry, all odd data, basic data. There we go, bounding box. So you can see where it is. Oh, all right. Well, it looks like we kind of lucked out. Although it also looks like it's not perfectly aligned, right? So the symmetry axes aren't perfectly aligned with respect to Z. So if we were going to do anything with imposing symmetry on this, even if we got it centered properly, we'd still have some issues. Since what we're going to be doing is looking at flexibility and dynamics, it's not going to be, we're not going to be imposing any symmetry, so it doesn't really have to be centered properly. So that may not be an issue in this particular case, but if you wanted to make symmetric data, you'd probably need to readjust this for the symmetry axes. I can go ahead and do that with the whole SS8, and we can just take a look at how that works. So let me go back to Chimera for just a second. All right, so we're going to load the whole 1SS8 and save that because I didn't have the whole file before as a PDB. 8 full PDB, and we'll just save that one. And I don't want to do selected atoms only. That should be okay.
Tried the chains option and it looks like it worked very well.
Ah, when you were generating things? Okay.
Yeah.
Good. I'm sure it was added for pretty much that reason. I probably was the one who added it, but it was probably 15 years ago, so just don't remember. Oh. I'm not sure I actually, yeah, I did. Okay, all right. Let's close the session. I'm just going to quit. Fine. All right. So we should now have 1SS8. Oh, where did I put it? Let me do it again. Well, I saw it, but what is this? A full? Oh, it's on the desktop. All right. Okay, so now I've got the full PDB. So if we want to make any adjustments to this, we can use the centering that we have to do for this as adjustments for the other HDF files. So I made all right. Let's go back to the PDB to MRC, and I made one for other. We'll go ahead and make one for B2. And we'll go ahead and make one for A. All right. A, B2. So I'm not necessarily doing all this stuff in the most efficient way. I'm trying to kind of balance it with showing you guys things which might be useful to see. So even though you're right, I mean, we could probably make it work with E2 PDB to MRC with just picking the chains. We might still have the sort of centering issue. So how do we tackle that in this situation? So I'll go ahead and we'll go ahead and run the E2 PDB to MRC on the full map. The issue that we're going to run into is that since we took out parts of the molecule, if we try to center it, it's not going to center properly. So we need to have the full biological unit without anything missing to figure out the correct coordinates for getting it centered. So that gives us a bounding box. And then we can see the atomic centers at -43.8 for the whole thing. So we can then do that amount of shift on the x-axis in the other structures. And since I had 1 angstrom per pixel, that shift should be the same in pixels as it is in angstroms. So we can now say E2 proc 3D.py. We'll go ahead and give it another name. I'll add a center to it just so we have a complete history of what we've done. If you overwrite the output files, I mean, it'll work fine if you overwrite the output files, but then of course, you'd have to go back and rerun programs if you wanted to recreate things. E2 proc 3D, 1 SSH to a send, trans 43.8.800. The other thing I'm going to do here, and I didn't do this when I was running the PDB to MRC, is specify how many bits to use in the representation for the file. If I'm gonna tell it to use only an 8-bit representation. This is using the new syntax that we just added after that the compression paper was published. So if you put a :8 at the end of that won't be part of the file name, but it will only preserve 8 bits of information in the signal part of the data. Well, we'll take a look at it in a second. Let me go ahead and do it for the other ones, and then I'll show you what I mean. Okay, so now we can see the A, and we can see the A_sen, and the B_sen, etc. And you can see that the file I created with the PDB to MRC was 64 megabytes, but the centered version is only 162 kilobytes, and that's because it's using only 8 bits, and it's compressing the results, and there's a lot of zero stuff in space. So if we open up all of these centered ones, B, and then other, we should see them all matching up pretty nicely. Now we can see the thresholds don't seem to match up perfectly. And the reasoning for that is that it's using a different threshold for each one based on sort of how much of the volume that it's occupying. So we can see here, the isosurface threshold was 0.027. Here it was 0.027, and here it was basically 1. right? So if I change the threshold to all for all of them to say 1, actually make it a little less than 1. Let's go ahead and make it 0.5 for all of them. So I can actually do that here using the convenience operation here. If we select all objects, I can say 0.5 here, and it should adjust all of the isosurface thresholds to 0.5. Won't show up until I wrote. Oh, there we go. Okay. Oh. All right. It worked, but it seems like the threshold. Oh, interesting. The density range seems to be different for 2 of the subunits. I wonder why that happened. All right, let me just take a look and see what happened there. See, sigma 0.3.006. Oh, it was fine before I adjusted the center. What was, all right, I'm wondering if there's something wrong with the :8 that I was, the compression that I told it to do. I wonder if I updated my code recently. So the :8 was something that we added recently, and it's supposed to preserve the density values without modification, but something a little funny is going on there. All right, I'm going to do it again, but I'm going to just leave the files full-sized. Let me remove the existing files just to make sure we get pristine copies. And we'll get rid of the :8s. I'm going to have to check that later. It should have worked fine. I don't want to recompile while we're doing this, though. Okay, so now we should have three different densities to work with. I guess we could do the same thing with the full one as well. Yeah, let me do the full one too. Just to show the alignment thing. All right, so let's see. Oh, yeah. Okay, yeah, we have a quick option in E2proc 3D for fixing the alignment if it's just rotated around the z-axis. So if you have something with C-symmetry, which doesn't have a specified orientation around the z-axis, and you want to shift to D-symmetry, you can use this option to sort of quickly do that. If you want to do, oh, sorry, no, sorry, just using that align C to D. Otherwise, we have to use E2 Sim Search 3D to find the correct orientation of the particle. And that takes a few minutes to run, so I don't want to actually run it right now. But that'll actually search all of the different Euler angles for the best symmetry orientation, and then tell you what rotations to apply. Again, we don't actually have to do that this time because we're going to be doing an asymmetric reconstruction because we're looking at things moving and that sort of thing. So the next thing we need to do is now actually do some Python coding so we can put these things together and generate what we're after. So I think we will we'll look at the rotation first, and then maybe we can look at the addition of say CTF or something like that. So let's run Jupyter Lab session. Let me do that. This is a lot wider than it needs to be. There we go. Oops. And we'll go ahead and read in files, in data 1 SS8 a.hdf. This is 8. No, go with the centered versions. Okay. So all these things should be EM data objects now. And if I say, let me go ahead and open up one of the E2 display sessions so we can do some interactive graphics. You recall that E2 display server thing, which gives us that other window. And then we could do something like E3 display A plus B plus C. And we want to say that it's volume. I think it's volume. There we go. So we should have gotten a window. Oh, there it is. There's the window. We can adjust the settings a little bit. And we can see that it looks reasonable. Okay, so that's the sum of the 3. So we can easily add or subtract different pieces as we like. Sorry, this again, we've got the display resolution thing that I talked about last time, where I'm using a high resolution display setting. I can adjust that again. Let's see. I need to use a low resolution 1080p mode if I wanted to scale properly. I thought we did something to fix that. Maybe I still haven't updated. We'll do that. Now, try it again. Oh, hang on. Oh, changed here too. There we go. Okay, so now we've got now we've got the whole structure. So what we want to do then is manipulate the orientation of B and C a little bit. Or so I actually C we were gonna leave in or take out, and B I wanted to change the orientation in some fashion. So let's see what happens if we just start with this. All right, let me change my display, and we'll display. So each time I did that, because I'm using the 3D display widget, each time I did that, oh no, it did. All right, it actually did it correctly. It only added it once to the widget. I was afraid that it would have made another copy every time I told it to display. We have to figure out which axis we want to rotate around. So let's display A, B, C like that. And I'm going to. Yeah, all right. Let me separate it out so I can give each one a name. A volume, and we'll call it A. And E3 display B volume, and give it a name. And E3 display C. Give it a name. Oh, actually, it's going to be the name of the window. I need to give the name of the data object or test. So just to clarify again, probably need to simplify this a little bit. Clarify again. So this is the data object. It's a volume representation. This is the name of the window that it's going to get put in, and then this is the name of the data object within the window that it's going to go in. So let's see if that works. Okay, so it made a new window because I gave it a name test. So you can see there's the name test up there. And if I open it up, you can see now I have A, B, and C, which I can now control individually instead of just the whole thing. So I can rotate this around. Now, again, we have the issue that the isosurface isn't the same. So the isosurface here is 1.3, 1.35, or 4.7. So let's set this to 4.7. And this time, now it's looking good. Okay. So now what I want to do is I want to figure out what Euler angles I need to use to rotate this in some reasonable fashion. So what's it going to do? So let's pick one of these. We'll pick A. And go to the basic properties for A. And here's the orientation right now. Let's go ahead and reset all of the orientations first. Okay, now I'm going to pick A, isosurface ray, pick A, and I'm going to try rotating, say, phi. Okay, you can see it's in the bottom there. Maybe I should do B instead of A because it's the one on the top in this orientation. So let's do B, and we'll rotate it there. Okay, so B, so that's probably not the orientation we want to use to rotate this. Now we can try rotating altitude. That'll be rotating around the x-axis. And we can see that's rotating that way. So again, that's maybe not completely spectacular, right? That's going to kind of rotate it so it collides a lot. I'd really kind of like to rotate it towards the middle. So to do that easily, I probably would have wanted to pick a subunit, which was oriented already on the x-axis. So if we want to do that here, we're going to have to be a little trickier. So I want this rotation to basically rotate towards the middle. So the first thing I need to do is figure out what orientation is going to put that roughly on the x-axis. So let me say I want to be able to do negative rotations here just for convenience. So I'm going to, well, that's fine. So I'm going to rotate that around, maybe there. That's pretty good. Okay, so that's minus 62.5. And then if I put an opposite azimuth in, 62.5, it's going to go back where it started. Okay, so why is that? Because this is a ZXZ rotation. So we rotate around the Z-axis, then we rotate around the x-axis, then we rotate around the z-axis again. So if these are basically just counteracting each other. But if I do an altitude rotation now, it's going to be rotating around the rotated coordinate system, right? So it does the 62.5, then I rotate the altitude, and then it does the opposite z rotation. So that should, well, kind of right. Maybe I got.
Shouldn't the first one be the minus 62.5?
Maybe you're right. I think you're right, Phil. I think I got it exactly backwards.
Because you got the 62.5 to get it to that location, but as comes first. So
no, I understand what you're saying. Thank you.
Okay.
You're correct.
Yep.
Okay. Oops.
Huh.
All right. Maybe not quite correct. So you can see how figuring out these Euler angles can sometimes be a little bit tricky. All right, so what are we getting here? All right, let me put it back where it was again. And that's doing that. Oh, maybe I want to put it, oh, yeah, if I want to rotate it towards the middle, I want to put it on this orientation, not the other one. So it should be the 90 minus this, right? So I want 27.5 instead. So how quickly can you think about Euler angles in your head? Ah, there we go. That's the one I was after. Okay, So that's not too bad anyway. Now it's kind of rotating towards the middle, and you can see we're still going to have some intersections between various parts of the structure there as it rotates like that. But maybe that's all right. We don't, we're just doing image processing here, so don't really care if it's sort of perfectly a perfectly good molecule, right? A little bit of error there is fine. All right, so what we need to remember now is this 27.50, 27.5 thing, so we know what angles to generate. So we want to use that here. So we're then going to say, CA. All right, let's just start out with this. B is equal to, all right, no, AA is equal to A dot process XForm transform. Again, you remember this really complicated process. Now, I think there's actually easier. I think we can just say A dot rotate and make use of that sort of shortcut in EMAN2. The only trick is when you use rotate, it rotates in place. It doesn't create a new object. So then we'd get interpolation error building up as we rotate it over and over again. So, all right, maybe I will do it that way. So we'll say AA is equal to A dot process XForm. Maybe we have an easier one. Is there a rotate? I just hate the syntax of the generic transform object, because then you have to type a whole bunch of parentheses and curly braces and stuff. A2 help. Oops, py processor XForm. Now it looks like we have to use X4. No one added a shortcut for just rotate. We've got translate shortcuts, but no rotate shortcuts. Oh, okay. Hold on. For XForm, instead of passing in a transform, we can pass in alt as phi. That's the shortcut. Okay, let's do that. Alt minus 27.27. Oh, sorry, that's as minus. Sorry, was it minus or plus there? Plus 27.5 altitude, and we'll go ahead and just do a test first. We'll make it say 15 degrees, and then phi minus 27.5. We want to replicate that for B and C. Oh, no, I don't. I only want to rotate B. Sorry, not A. Silly me. Okay, so we're going to rotate B. We're going to leave A alone, and we're going to leave C alone. And then we're going to do the sum. So E3 display. Let's go ahead and do the same thing we did up here, but I'll go ahead and I'll just add it to the same space. Yeah, like that. Oops. And we're going to say BB instead of just B, so it's a different volume. Give it a different name. All right, there we go. Okay, and you can see it's rotated. Again, the isosurface threshold has changed again, but that's fine. Bring this to the front too. And if we turn off B, now we can see that how it's rotated. So not a biologically realistic rotation or anything like that, but at least it's something. So we can now rotate that subunit by some amount that we like. And I would say maybe we can take it, if we want to really have a nice extreme motion, we could make it up to maybe 15 or 20 degrees, probably no more than 15. All right. So the goal now is going to be to create a test data set, which has random rotations of this B subunit ranging from 0 to 15 degrees. I guess we could go from maybe -5 to 15 degrees or something like that. We can rotate it the other direction too a little bit. With the third subunit, the A subunit, sometimes present or sometimes not present. So let's say randvol, and we'll, and this won't need any arguments. Say return is equal to A. Okay, we want to do it randomly, right? So let's compute the values first. Just to keep this in a sensible order. And I think we want range. Rand range. No, that's from a range. Sample uniform, maybe uniform. Yeah, we'll just do a uniform distribution. That's good. And I guess for the other one, we can just say random. All right. So we're going to say the angle is going to be random.uniform -5 to 15, and we'll say that C present is going to be 0 if I'm remember this new construct, 0 if random dot random is less than 0.5, else 1. I think that's okay. Oops. Oh, it's only defined in there. What am I doing? We get a 0 at some point. There we go, 0. Okay, good. So now we will take. Let me get rid of this help up here. It's taking up too much space. Now we will take our code here, rotation code. That in here, and we're going to rotate here by angle. And then if cpres return B plus A plus B plus C. Actually, it's not cpres, it's apres, just to be self-consistent. If apres else return B plus C. Okay, so now we have a nice function that'll generate a random volume for us with the properties that we're looking for. Now, the next thing we need to do is make projection in a random orientation. I guess the question is whether we want to only make one projection for each volume that we generate. That'll be a little more computationally expensive if we do it that way, or whether we might want to make, say, several projections for each volume. Yeah, we can do it however we like. Let's try it the expensive way and just do it that way for the time being. So we'll say okay, so the next thing we need to do is figure out how to generate random orientations, right? So how do you generate orientations in EMAN2? So there's another type of one of the types of modular classes is orientation generators. And this will give you orientations in using different schemes. So RAND will just sort of give you completely random orientations. EMAN2 will generate orientations using EMAN's distribution over the sphere scheme. Now you might say, why can't I just say take the Euler angles and generate random values for all the Euler angles? Well, that won't actually give you a uniform distribution on the sphere. So you have to be really careful when you're trying to generate random orientations. There are a few strategies for doing it. One easy way would be to use, say, quaternions, and you can generate a random quaternion vector and then a random rotation around the random quaternion vector. And I'm pretty sure that gives you a random set of orientations. Or you can sort of take the risk out of it and use one of these existing things. If we get asked for a little more help, sorry, that's just not scaled very nicely there. Now it's fine. RAND, you can see generate random orientations within an asymmetric unit. We're not going to give it any symmetry. It's just going to be C1. Anyway, so we can go ahead and do that. Now, how do we actually make use of an orientation generator? What we have to do is we have to make a symmetry object, and we have to ask the symmetry object to generate our orientations. That's the strategy that EMAN has used. So we have to say sim equals symmetries.get C1. And that will give us a symmetry object. Okay, we say help on the symmetry object. You can see that there's a bunch of different things you can do. One of the things you can do is generate orientations. Okay, so back to the orientation generator that we were looking at here. So for the random orientation generator, we can tell it whether we wanted to generate all 3 Euler angles or just the first 2 Euler angles. And we can tell it whether we wanted to include mirror values or not. So in other words, you want to generate stuff from just half of the asymmetrics, the unit sphere, or the full unit sphere. And then we can tell it how many values we want it to generate. So it's going to give us a list of different transformation objects. So I'll go ahead and just generate all of the orientations at once, and then we'll use the orientations to generate our projections. So here we will say orts is equal to sim.gen orientations, right? So that was from down here, gen orientations. And we need to give it a generator name and then any parameters. So the generator name is going to be rand. That's what we're looking at the command line. And then parameters n, let's make, say, 1,000. And include mirror, yes, and phi2. We'll go ahead and do that as well. Okay, so that should, well, let's see, what did I do wrong? Oh, it's not phi2, what was it? Oh, no underscore, just phi2. Okay, so that should give us orts, which is a whole bunch of transform objects in nicely distributed orientations over the unit sphere. So, and if we do len of orts, it should be 1,000. Okay, so that gives us 1,000 random orientations to work with. So we have to decide sort of how many particles we want to generate. So thousands, maybe not. Now let's start out with 1,000. That's not a bad starting point. All right. So next thing we need to do is make projections. So we can do help on one of the EM data objects. Dot project. So I happen to know the name of the method. I don't want to look through all of the methods that are available in EMAN2. There's a method called project. So just like all these other modular classes, the project method takes the name of a projector and then a bunch of parameters associated with the projector. At least that's one of the forms. Projector name, parameters. There we go. Parameters. So we can take a look here again, command line, and instead of getting help on orientation generators, we'll get help on projectors. So there are several projectors available. There's the standard, which is just a real space projection. There is Fourier gridding. There's one that a guy named Chow wrote. There's one that Paul Penchek wrote. There's a Gaussian Fourier transform method. So there are various projection methods available. Normally, we use standard, which is just real space projection. Now, you might say you do your reconstructions in Fourier space. Why don't you make your projections in Fourier space as well? And it turns out there's sort of an asymmetry computationally in those two processes. When you make or do a reconstruction, you're taking a whole bunch of different slices and you're inserting those slices in Fourier space. And each slice has sort of a different orientation. So if you look at just one voxel in Fourier space, there's a whole bunch of different slices which are all contributing to the value of that voxel. So when you interpolate, you're using some sort of interpolation kernel, like say a Gaussian interpolation kernel. So you're pulling values in, sampling that Gaussian kernel for that one voxel from all the different slices that are some distance away from that voxel. When you make a projection, you're taking a single volume and you're interpolating a value in between voxels. So the interpolation, even if you use the same interpolation kernel, you're only sampling that kernel at like the 8 neighboring points around it. And that means that it can produce some funny sorts of artifacts if you look at the projections in real space. So you can make projections in Fourier space, but they often turn out with more artifacts than you'd like. So even though it's a little bit slower, we usually make our projections in real space. It also helps prevent iterative model bias from building up. If you do your projections and your reconstructions all in Fourier space, then if you iteratively, if you make projections and you determine orientations, and then you do a reconstruction, and then you make projections, and so if you iterate through that process a few times, you can wind up with the Fourier objects, the Fourier artifacts getting reinforced as you iterate the process. Whereas if you do one in real space and the other in Fourier space, they sort of cancel each other out. Not exactly, but conceptually they don't build up. So we should be able to take a volume. We'll just take A and say project standard, and then we need to give it an orientation object. So we'll just use one of the orts that we already generated. I'm just testing to make sure this works the way we expect. So we'll use the first orientation that we generated like that. And that should give us an EM data object out. Okay, so that allows us to make a projection. I'll do this just to show you what it looks like. E3, and I won't go too much longer. I know we've been going an hour already. Display P image. Okay, so there's our projection in a random orientation of just that one subunit A. Feel free to speak up and ask questions if anything I'm doing seems funny or confusing or anything like that. I realize I'm going through a lot of this stuff kind of fast.
I fell a little behind. Would you mind uploading the notebook at some point when it's finished?
Yeah, no, that's fine. Yeah, I'll save the notebook when I'm done, and I'll post it I'll post a link to it in the YouTube video.
Thank you.
Yep. Let's see, untitled. Let me just rename this now so I don't accidentally overwrite it later on or something like that. Rename. Sim data. Okay. So that lets us make one projection. And I will say for orientation in orts, or maybe we'll Yeah, we'll just do that. Imports. V is equal to randval, and P is equal to V dot project, and the orientation. And then last but not least, all right, let's do this. We'll say IO enumerate ports. So that'll give us an index number to use. That way we won't, if I append to the end of the file and then I run it multiple times, then I'll end up with a file of 2,000, 3,000, 4,000, whatever. So this way we'll kind of overwrite if we do it multiple times. And then we'll say p.write compressed projs.hdf, and we'll write it to position I. Okay, so that should generate 1,000 projections and random orientations with random relative orientations of subunit B and random presence or absence of subunit A. And it's going to take a second or two to finish, but I don't think it'll take too long to finish. The volumes are only 256, so they're not too terrible. Let's go back here while we're waiting and display. We'll run another E2 display and we can sort of see what it's got. Oh, 81. Okay, so it's going to take a little while. I'll just open up the ones that we've got so far so we can sort of see. Right? So here are all the projections that it's generated so far. The box size is maybe a little bit tighter than I'd normally like, but it's probably not too bad. For the purposes that we need to use it for the looking at dynamics, should be fine. Okay, so I will go ahead and, oops. I'm not sure what I did to cause it to do that, but it doesn't really matter for what we're doing right now. I will go ahead and rerun this for maybe say 5,000. I'm just trying to think how many we want to have for the testing with the Gaussian mixer model. We don't want to have too many. We don't have too few. All right, maybe we'll make 10,000. We don't have to actually use them all if we don't need them, but that way at least we've got them all. So if you want to participate in the testing of this yourself with the Gaussian mixture model stuff, which we'll do next week or the week after next week if we want to do the CTF first, then go ahead and you can run the script yourself on your own machine and you'll get different orientations than I did, but it should be functionally equivalent. So I'm going to change this in the script after it finishes running. We'll take it up to 10,000 and run it again. And clearly it'll take a little while for it to run because it's making a new projection for each one and it just takes a little time. And since we haven't talked about CTF yet, next week either we can talk about the CTF and adding noise and stuff like that to make proper projections, or we can just jump into doing the GMM on the noise-free data, and then we can talk about the noise thing later. We'll see how things go. The CTF and noise stuff actually shouldn't take very long now that we've done the tough part. I mean, getting all these orientations and stuff like that right, that was really the hard part of this process. The CTF can be handled in just a few lines, but I don't want to take any longer today.